Thank you everyone for joining this session and how to tune your SQL dedicated pool and enable its full potential. So my name is Tiago Balabuch and I am a cloud solution architect at Microsoft with more than 10 years of experience working with data. So I came from the relational database to the analytics, and I'm also like so much the big data and all this stuff. So I have lived in 4 different countries. I'm Brazilian, but I'm living in Portugal right now. And you can find me on the beach. So every time that I have a spare time, I go to the beach. So this is a little bit about me. How about you, Filipa?
Hey, good morning. My name is Filipa Lobão. I am a cloud solution architect on data and analytics at Microsoft. I have about 5 years of experience in data-related roles, and my background is as a BI developer and ops on premises before joining Microsoft. I have a bit of a different background from the typical IT personnel because my studies were in biology. Then I was a cabin crew and I thought, okay, let's try IT. And it ended up pretty well. So I'm here now and I love outdoors. So you'll find me outdoors doing anything sports related. That's me.
That's great. So what we have prepared for you guys today is we are going to talk a little bit what is the motivation for this session, the business case. We are going to see the architecture of the dedicated pool, how it is important, as well table distribution, index, data movement, materialized view, workload management, and a lot of stuff. It's too much to condense in so short time. So let's get started.
Yes, it's 45 minutes. It's definitely not enough or a lot of time, especially for such a complicated and complex topic like performance tuning. We have a lot of cases where customers reach us for poor query performance. They have difficulty in achieving a performance benchmark. They have usually on-premises to cloud migration scenarios. And the most common cases, I would say, are the slow query executions, the processes that take a lot of time to run comparing to what they had before. People aren't sure how to tackle those and monitor use cases specifically. And well, on-prem it was running quicker, so we want to make sure that you get the best of the engine and its advantages and top performance. So that's why we chose to present this session, because it's very relevant on performance tuning. Is a very relevant topic, especially for whoever is new to Synapse. It's important also that you have a good understanding of the environment that you have, that you track the most used objects, for example, and have well-defined priorities on tuning the performance of your SQL dedicated pool. Okay, let's look a little bit of how this works. So Synapse Analytics brings together the core elements of a modern cloud data warehouse under the same secure and integrated workspace. It incorporates 2 of the most successful analytics engines, the SQL and Spark. It provides also pipelines for data processing, as you're probably aware, and it uses an integrated data lake storage. So if you need something like predictable performance and cost, then creating a dedicated SQL pool to reserve processing power for data stored in SQL tables, it's the ideal for you. But however, if you need to accommodate like unplanned or bursty workloads, then the serverless SQL endpoint is also a very good option here. And let's dig in the architecture and explore the different attributes of Synapse and see how they come together to help you optimize your analytics. So the architecture is a bit different. Let me just go. Yeah. So we have here the control nodes. This is like the connection and the tool endpoints that coordinates the compute activity. So it's the brain of the massively parallel processing engine architecture. It's in the front end to what interacts with applications and connections, and the distributed query engine runs on the control node. So this is responsible for optimizing and coordinating queries. However, in the compute node, we have several SQL databases. So it's the muscle of the MPP architecture because it provides computational power, handles query processing, and gives the user the ability to scale up or down. And the number of compute nodes that you have can range from 1 to 60. So the compute node works as a VM, hosting two key components of the SQL data warehouse. You have the SQL database and the DMS, the data movement service. The SQL database crunches the data and the DMS moves it. So the primary function of the SQL data warehouse is to optimize and manage any incoming work. So it parses and creates query plans.
Filipa, just a second. So, Andy, can you confirm that you guys can see the slides? Because I've seen in the chat some questions. Okay, you can see the slide.
I have a couple of thumbs up. Cool.
Sorry about that.
No, that's cool. Thank you. So like I was saying, the DMS will coordinate the data between the compute nodes. But how does the MPP work? So it's a divide and conquer concept, right? So it uses many separate CPUs running in parallel to execute a single program. And it also works on a shared nothing notion. So each CPU has its own memory and disk. And then you have 60 databases that are equally divided. Okay, let's jump on the table distribution. Why is table geometry so important? So for an app, for us, for the customer, it looks like only the table is being created, but actually behind the scenes, the data is being distributed. So it's important that you choose the correct distribution to your data, to what makes sense to the data you have, to the amount of data, to the type of data, and how much it's used, for example, and make sure like you get the top performance that the engine offers. So round robin, it's the default, and many users are not yet aware of it. So every time you create a table, if you specify no geometry, it's going to be a round robin, which means that data is evenly distributed across the nodes, but with no order. So it's at random. So imagine you have 60,000 rows that are just filling the distributions one by one until it fills the whole distribution, the 60 distribution. The problem is that the data is going to be spread across the distributions randomly. So we don't really know where the data is, and this may cause query performance issues. However, it's a good way of loading data. The other option we have is hash distribution, which is ideal for distributing, for example, large fact tables. The data will be distributed across nodes, and it's based on a hashing algorithm. And this is based in a column that is always used for the same distribution. A better performance will be achieved if it's properly distributed based on the front column. You have multi-column distribution enabled as well, similarly to, for example, engines like Netezza and Teradata. And when migrating to Synapse, you will have to select one of those to distribute data. And finally, the replicated table. It's a full copy of the table in each node, in each compute node, sorry. And it's good when the goal is to maintain a copy of the table in each of those nodes. So you don't have to think about distribution or data movements in this case. And let's deep dive on the three types of table distribution. So we have the round robin, like I mentioned before, data will be distributed evenly across nodes. It's an easy place to start because you don't need to think about or know anything about the data. But it comes with a cost. It's simple to use, but it incurs more data movements at query time. So a good starting point would be to use it when you have no obvious joining keys, when you have no candidate column for a hash distribution table, or when the table does not share a common join key with other tables. If the join is not as significant, has other more important joins in the query, when the table is, for example, temporary staging table, or, oh, sorry, and that was it for the round robin. And for the hash distributed table, we have this distribution ideally for large fact tables with highly distinctive values, like, for example, minimum 600 distinct values. But there is an issue here, like data, give me a second, sorry. First of all, you should not use nulls, or you should have very few nulls. You should minimize the data movements as well for this type of data distribution, and also choose a column with the data that distributes evenly. I'm just going back, sorry. Okay, so there is a problem here for data skew. It should be minimized at max because it means data skew means you have an uneven distribution of rows across the 60 distributions. In order to avoid this, you have to pick a column that has less than 60. You have to pick a column that has more than 60 options. So imagine you pick a column for hash distributing the data that has 50 values. For example, the states of the United States of America. So it means that not all states will be distributed by one of the distributions, one of the 60, because it's 50. So you will leave 10 with no value. So it's not a good column to distribute the data for. You should pick up a column that actually allows this distribution to occur from the 6,000, from the 60 distributions you have more evenly as possible. So never like a round robin style. Like I mentioned for the nulls, like you should avoid this because otherwise you will have one of the distribution only for the nulls will be heavily used if you have a lot of nulls, which comes with performance issue. And then be mindful of negative if you have a lot of negative values, because this will also provoke data skew on the distribution. Okay, and finally the replicated table. So this is the type of distribution that will consume more space, but it's very useful on scenarios like star schema reporting, like if you have dimensions for describing entities about fact data, or if you have ETL master data, or common domain data during transaction loading, for example. I just want to leave a note here that actually, although there is a copy of every replicated table on every compute node, the engine doesn't technically keep a copy of the table at all times. So what happens is when the replicated table is created, the data is distributed in all the distributions available. But when we select from it, all the replicated pieces in all the distributions are combined, and the cached version of the replicated table is then created on each compute node. So this way, when you join the replicated table with other tables, we have a piece of this data in each compute node, and it decreases the data movement across nodes. So it's pretty useful for those scenarios. And another very important topic is the table indexes, which Tiago will present.
That's great. So we have to understand this architecture for Synapse dedicated pools. We have to understand this table geometry, but we also have to understand index and what kind of index we have in the dedicated pool. So the default index is the column star index. So we are having a high level of compression. It's best overall query performance. So, but we also have the clustered index and heap, and even more, we have no clustered index. So those type of index are the same one that you guys have been using on the SQL Server itself. But the difference here is the column star index being as a default. So every time that you create a new table, you will have, if you not specify the index type, you will have a column star index. And what is important to know about it? What is the column star index? So your normal index, let's say that your index are stored as a row by row. But when we use a columnar format, a column star index, we store as a column. And then we are able to improve compression. We are going to reduce I/O, and we are going to enable a batch mode execution. Batch mode execution is a difference from the row mode execution, because instead of doing row by row, we are going to get a batch almost 1,000 rows and execute every operation in this set. So that's where we gain performance. But column star index is a huge topic, and I want to give you a little bit concept on it because we have seen a lot of issues with column star index. So understand the terminology, the concept behind this is important. And here we go. So we have your data. Let's assume that you have a table with 10 million of rows. So what is going to happen when you are creating a column store index. We are going to divide this table into row groups, and these row groups will have the maximum of 1 million of rows, each row group. If your table has 10 million of rows, we will end up with 10 row groups. Then we have segments. Segment is your columns. Each column that you have in your table will have one segment. For example, if your table has 5 columns, we will have 5 segments. And the last part here, what we are going to do for each row group, for each segment, we are going to apply an algorithm to compress. And at this stage, we are going to have the column store index itself. So this phase here is where your index is ready. But we also have internal objects on this column store index called dictionaries. Dictionaries is where we store metadata of your data. And we have two kinds of this. We have a primary and secondary. Primary is going to work on your entire table, and the secondary is going to work in the specific row group. So even more, we have a delta store. Delta store is a place where we store your updates, your insert, your delete before we apply compression. Okay, so every time that we do that, we create, every time that we insert, update, or delete, we go straight forward to delta store, not to the column store index itself, because it's an expensive operation. We cannot do it every single time. So looking at the row groups states, we have mainly these 3 types. Open state means that I'm accepting rows. So in the end, behind the scenes, your rows are going to be stored in the delta store. And then we have the closed. I have reached my limit, it's 1 million, and I'm waiting for a back-end task to compress my data. And we also have compressed. Okay, now you have your column store index. Now you definitely have your index. It's important to understand because we have seen a lot of issues on it. So I will cover it in my demo. Let's just wait one more second. Even more, let's talk about these dictionaries. Let's talk about this trimming that we can have in your row group. So we have different ways to check the health. We call that the health of row group. So when we have no trim reason, that's the one we want to have most of the time. We have reached the maximum of 1 million of rows. We can also have book loaded. So when we are insert data in a book, we can have this state. So it's a good, and we want to see this as well. But we have seen some trimmings that cannot give you the right performance or the best performance. The memory limitation is one of the most common issues in your column store index. So it means that the user that is performing the creation or the rebuilding the index reached the memory limit. So be careful with that. Make sure that the user that you are using to rebuild index or create index has enough resource available for it. You can use resource class, or you can use workload management with high resource. We're going to see it as well. And that one, this dictionary size is when we reach the maximum of 16 megabytes in the dictionary. Doesn't matter if I have 100,000 of rows, or if I have 100 rows. If I reach it out to 16 megabytes, I will close that row group. So when it happens, basically when you have a lot of varchar or n varchar in your data types, many columns with that one, you will likely have this dictionary size in your table. How we fix it? Try to reduce the data type size. That's important. Okay. We also have introduced an ordered column star index, and that is fantastic because we are going to improve
I think we lost Tiago. Give us a second.
Oh no, Tiago's frozen.
Yes.
Sorry for that, guys. My computer just reboot. Sorry about that. I just moved to another room.
I thought you were going to the beach early.
So, can you hear me now? I got frozen there.
All good, all good.
Okay, good. Sorry about that. So the ordered column star index, it's going to improve your segment elimination and row group elimination. So we are going to create your index in a certain order. So you're going to specify a key and we're going to create it or rebuild it. Just a catch here is when you insert or delete or update new rows, they are not going to be ordered. You have to rebuild it again. Okay, so it's a great improvement of performance that we have seen in our customers. Also, so what determines performance of a column star index? The size of your row group. So we call that the row group quality. So try to have the maximum of 1 million of rows in your database, in your row group. So try to avoid memory pressure when you are rebuilding it and try to avoid the trims. That's the general advice that we can give you. So also the delta star, avoid it as much as possible. So delta star, it's a clustered balanced tree on page compressed. So you are going to read it from not the column star, but your clustered tree. So in the end, we have to read from the column star and the delta star. Avoid as much as possible. And every time that you perform a small batch or a single operation, we will end up in the delta star. So be careful with that. One thing that I want to call out is partition. So we have seen a lot of issues with partition. Customer that came from SQL Server on-premise or even Azure SQL database try to use the same approach of partition. But if you remember what Filipa said about architecture, it's important here. So remember, we have 60 distribution. Every distribution will have your own column star index in the end. So important to understand the minimum of rows to use a column star index is 1 million multiplied by 60. It means I need 60 million of rows in my table. When you partition at that table, you are saying, okay, for the first distribution, I will partition at it by any partition that I want. For example, if you want to partition for the last 5 years, you will have your first distribution partitioned by 5. In the end, you will have 60 multiplied by 5. You will have 300 partitioned data. So be careful with that. Too many partition is going to give you a worst performance that you don't want. So right now we have talked about these things, and another common issue is the data movement. And I will switch to Filipa.
Hello again. Okay, thank you, Tiago. So on the data movement side, you're probably aware that this is one of the biggest responsibles for performance impacts. Basically, the data movement service is a system-level internal service that will move the data across the nodes as necessary to run queries in parallel and return accurate results. So being one of the main responsibles for bad performance on query execution in Synapse, this will happen mostly when data is moved for incompatible joins. So for example, the tables involved in the join must be hash distributed on one of the columns participating in the join, or when you have incompatible aggregations. So when the data is aggregated on a column that is not the one used in the distribution, or also happens in redistributing the data. So for example, CTAS operation to a different table, geometry, for example, on query syntax as well for functions on predicate like where, over, outer joins, and for round robin tables. So any query that joins a round robin table apart from a replicated table. Okay, so let's see also couple of moves or the main moves for data for DMS operation. Like Tiago was mentioning, we have the partition move here, but this data movement is essential and also unavoidable query components in a SQL pool data warehouse environment. So the goal of understanding the different types of data movements and performance tuning is to reduce the number of rows and the amount of data that is being moved as much as possible. Welcome back, Tiago. So we should minimize the data movements by properly designing the tables based on the query pattern. So that's why it's so important to be aware of the table geometry and choose the right one. So the types, I am hearing myself in echo, not anymore. Okay, the types of data movements we have are shuffle. So it means that it redistributes a distributed table. And the redistributed table has a different distribution column than the original distributed table. These may be used, for example, when running incompatible joins or incompatible aggregations, and it can be solved by changing the distribution key. So if you choose the right one, like the right column to distribute your data, then you will not have this shuffle move anymore. And we will actually see this in the demonstration I will show later. This is also the most seen scenario for data movement that we come across. For the broadcast move, it means that moves the distributed data into a replicated table. So it's an operation that is frequently used when running a distribution incompatible join. And if you update the statistics, or if you replicate the table, then you can avoid this move. The partition move, like Tiago was saying, when you have a lot of partitions, if you move the data from a distributed table to a single table on the control nodes, this will happen. So this will be used for aggregation operations on the control nodes. And then we have the round robin move, where all the data gets distributed as round robin. It's not so common data movement, so it's not one of the most used or seen ones. And finally, the tree move, where a replicated table is moved to a distributed table, and usually means that you have out-of-date statistics or that the table needs to be redistributed as well. And we are going to jump on the materialized view next. Tiago, are you? Yeah.
Yeah. So materialized view, it's another way that we have seen improvement of performance. So why we have seen that? Materialized view, it's a pre-compute and stores your data, but it's a different from SQL. We maintain your actual data. We perform an update in your materialized view if your underlying tables were updated. So this is a benefit that we have seen. It's become more relevant when we haven't reached the concurrence. So every time that I reach or I request a query from application Power BI, and this query reaches a materialized view, it means that we are not going to have concurrence. This going directly to the compute node. So we don't have to perform any kind of operation. So it's something that we have seen improvements in customer using repeated queries like Power BI queries. They are always the same and so on. So how we can get these benefits from materialized view? We can use explain with recommendation and issue your query. So you are going to, in this example here, you are going to see what are the recommendations for these queries. In this case, we are going to see a materialized view. So this is something that we have seen in order to gain more performance of your dedicated pool. And we also have seen a lot of issues with workload management. I know that it's a huge topic. It's very confusing topic, but when we have this workload management, we can classify our workload. We can tell, okay, we are going to have ETL, ELT workload. We are going to have a report workload. We are going to have a marketing workload, or even a power user workload, and so on. We can give them some importance. We can give them some priorities. So, and then we are going to combine those things to say, for example, during the period, we know that during the morning, the market team has priority over the financial team. Okay, so that's incredible how we can speed up our dedicated pool based on our business. We also have isolation. Isolation is where we have seen a lot of misconfiguration here. So let me try to clarify one thing. When we have this isolation, it means that I will reserve a percentage of my data warehouse, my SQL dedicated pool, for that specific workload. Doesn't matter if I have queries, if I have some user requesting data or not, this will be reserved. So be careful with that. That's something that leads to a queuing in other workloads groups. So be careful with this configuration. So we have said a lot, and how we can monitor everything that we have said.
Yeah. So how do you basically get to know what's behind the scenes and put your hands on? So as many of you are probably aware, we do have something called dynamic management views. Those are system views that allow you to check detailed query execution, that track the life cycle and resource usage. So this allows you to monitor on the data warehouse directly. The benefits are that you see active query troubleshooting. You identify workload performance bottlenecks and get to tune them and work on them, because those give you extremely fine-grained telemetry for deep analysis. And also you can programmatically monitor this using T-SQL scripts or stored procedures. Another way, it's using log analytics. So it allows you to analyze SQL data warehouse and metrics. It can be streamed to Event Hub. It has customizable retention with Azure Storage, so it integrates with a lot of other Azure services, and it operationalizes the logs and metrics for insights. So I would say that the biggest benefits here are that you can get access to historical query troubleshooting. So this means that you can either see what happened, what was executed before by configuring, for example, the request steps or the exec requests that you can see in the screen. And this also allows you to have real-time monitoring and long-term. So it's very customizable. And the visualization options are also super user and customizable. However, like, the cost is controlled. So it means that if you just add these two, for example, these app requests and request steps, like you can see in the picture, then you'll have a very low cost. If you start bringing more metrics, then you have to be attentful of what are you adding and if you really need those. And it's a very good tool and very powerful tool for monetization. Also, you have the Azure metrics. So through Azure Monitor, it tracks the metrics that are related to utilization and security of your instance on Synapse. It allows you to export to Log Analytics for further analysis and is cost-free. So using the metrics here, you will have an holistic monitoring across all the Azure Analytics platform. It also gives you customizable charts and dashboards and allows you even to identify under or over utilization of your resource. So it will give all the admins the possibility to make an informed scaling decision. And we want to present you something that is pretty recent. So it's the Azure Synapse Analytics report. This was created in Power BI by some of our colleagues in Microsoft, and it was done to help you identify common issues that may be present in your databases and can lead to performance issues. I know Tiago will focus on this later. I hope we have the time. But basically, the report focused on known best practices that Microsoft identified for all the SQL dedicated pools in Synapse. And following these best practices, it will help you to get the best performance of the solution, obviously. It provides you the main pages like issue tables, where you can see all the data skew, large replicated tables, missing statistics, outdated statistics, and too many partitions, for example. And it gives you also table detail and external table detail. This is all done using the DMVs. So I would say it's a very quick way of having a broad understanding of what's going on behind the scenes, like on your database, like what are the tables that have the most issues, or what are tables that are being so impacting performance, and that you can tune and work on. And the most common issues that we have on performance, Tiago will explain now.
Yes, so these issues that we have seen in our customers are the most common. So first one, and the top of them, is the data movement. So data movement is something that we have to worry about that. We have to look at it, okay? So, and the action to it is look at your table geometry, look at your statistics. So update your statistics is a part of your maintenance plan. So actually, currently, we don't have the auto-update statistics, so just take it as usual, okay? So we have seen the TempDB usage caused by data movement. So when you move a lot of data, you are using TempDB. You are going to see your TempDB full, but in the end, it's because you are moving a lot of data. We have seen query queuing, again, misconfiguration on your workload management. Look at it, try to understand it better, and so on. So high CPU, optimize your queries, use your techniques that you have learned from the SQL Server. Build replicated table. Make sure that your replicated table is as smallest as possible, is smaller as possible. And the second one, in my view, is a bad quality column star index. So everything that I said before, check the minimum of rows, try to use order column star index, and so on. Okay, so these are the scenarios that we have seen in our customers. So let me make a quick demo for you guys on everything that we have said. Let me share my screen. So this is the Power BI report that Filipa mentioned. We have been using this in a few customers, and it's helped a lot because most of the issues are here, and you can quickly view it and take an action. For example, I have this two-man partition. So if I hover my mouse here, I will see a little explanation about it. When I click in this issue, I can see what is happening. So my table is that one. What are the row group streams reason that we have in this table? And I can go even further. Right click on the table, drill through, and table details. So, and here we have a view for this specific table. And we can see that the issue that we are having, it's too many partitions. Why is that? I have 13 partitions in my table. I have a lot of memory limitation trim here. I have a lot of open row groups. So that's a bad performance. If you query this table, if you make a join, you will not have the best performance as possible. How we fix it? So I just created this notebook to help me out with this. So I have a few views that's going to give me details about the health of row groups. So I will share this notebook later with you guys. There is a link to download this view and you can reproduce it yourself. So my table, look at that. I have more than 600 open row groups. It's bad. But one thing that I want to highlight is the average compressed row. I only have this 200,000 rows. So, 200,000 rows. So what we can do as well, I can check this details of this compression, or even if we have this memory limitation here, we have also, look at that, the amount of rows that it's not even close to 1 million. We can improve it. We can get more benefits from it. So you can see a lot of open here. It's a bunch of them. Look at the amount of rows that we have in each of one of these row groups. So basically, this is selected just to tell me how many partitions I have. So a simple fix on it. Remember, I have a table who is distributed in 16 distribution. Okay. So every time that I partition that, every distribution will get partitioned. In this case, if I have 13 partition, I have to multiply by 60, multiplied by 1 million. That's the minimum of rows evenly distributed to make sure that I have the right or to get most benefit from my column store index. So what I have to do, in this case, I will remove my partition because I don't need, if we come back here, I can see only 100,000 of rows. Why should I distribute my data? If I divide it by 60 distribution, I will get only 2 million of rows in each distribution. That is not a large number of it. Okay, or at least I could partition that in 2, not in 13. Okay, so what I have done, I have created this new table. So now I'm going to compare. This is my previous one, and now I'm running the new one. I created this. Look that this number with this number, it's much better. I only have 2 open row groups. And if I look at the maximum row compression, I have reached 1 million. It's a totally different from here. Okay, we can see some details here, the open row groups, and again, I will run this. This is a new one, just to make sure that you guys have this. I only have 2 and 3 reason, no trim. I have reached my limit. That's perfect. So what I have to do, just switch tables. I create a new one using a C-test and I'm switching tables. Now I can come back here. I can, refresh my data set. Come back to my table issues. Let's see. And it should be gone. Power BI sometimes trick me. I will refresh this one. Nothing there. Let's try this again.
I think we've just got a few seconds left.
Okay, sorry about that. So that's what I wanted to show you guys. Sorry, I will not have time for Filipa demo, but we will give you a notebook, then you can walk through it later. So yes, this is how we can improve performance in our SQL dedicated pool.